Hello everybody, and welcome to our video reviewing some of the features of the ruler function that we talked in class about. So we're looking at page 61 in the workbook, and just to refresh your memory a little bit, we had a definition of the ruler function that looked like this. Notice in this definition that we get different results depending on whether we plug in irrational or rational numbers. In particular, any irrational number that we plug into this function is going to give us 0 as an output, and any rational number that's in reduced form p over q, we're effectively going to ignore the numerator and get an output of 1 over q. Now in class you plotted some points on this function already, but let's review that process just to make sure that we understand what this function is telling us. So if we take an irrational number like 1 over the square root of 3, for example, this function is telling us that we should get 0 as an output. 1 over the square root of 3 is about 0.577 as a decimal, so to plot this point, we would find this number on the x-axis and this number on the y-axis, and we end up with a point that's right here. Okay, and any irrational number is going to land right on the x-axis, just like that 1 over the square root of 3 did. Now, more interesting is what happens if we start plugging in some rational numbers. You already did this, but again, let's take a minute just to review that. So when we did this in class, we started with rational numbers that have smaller denominators. Okay, for example, maybe 1 over 3 and 2 over 3. Okay, so since those two rational numbers have the same denominator, our formula for the function is telling us we should get the same output. 1 over 3 in both cases. Okay, where are those points? Well, the first one, we plug in 1/3 and we get out 1/3. So if we go over to our picture and find those two numbers, 1/3 is here and here, and so the point would be right there. Okay, and similarly, if we want to plug in 2/3 and get out 1/3, we can find those numbers. 2/3 is here, and so when we plot that point, it would land right here. Okay, so 1/3 and 2/3, when we plugged those in, gave us these 2 points, there and there. Okay, and then you went on and plugged in points that have a denominator of 4. Okay, we're skipping over 2 over 4 because that's not in reduced form. If we plug in 1/4 and 3/4, again, we're going to get out 1/4 in both cases. And if we plot those 2 points, they end up being here and here. Okay, a little bit below the points that we plugged in for 1/3 and 2/3. And we kept going. Okay, so the next points up would be denominators of 5. And they're also going to all have the same output. Okay, so if we plug in 1 over 5 or 2 over 5 or 3 over 5 or 4 over 5, we're going to get out 1/5 for all of those numbers. And if we plot those points, they're going to be here, 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 and here. So you can notice a pattern here. The bigger our denominators get, the closer to 0 our outputs become. Okay, now if we kept going, we would keep plotting points here, and what you might notice is that our points are going to keep getting lower as our denominators get bigger. So there are a lot of points on the graph that we can't see yet, but they're all going to be down here. Every rational number that we continue to plug in is going to be down here, and all the irrational numbers, like we talked about before, are going to be right on the x-axis. So in the next video, we're going to start exploring the question, might this function have a limit? Okay, and we're going to try to convince ourselves that if we pick a point, the limit of this function is actually 0. The basic reason for that is the fact that there are so many points, so many output points of this function that lie close to 0, below all of the points that we've drawn.